Welcome to Module 6, Lesson 25, Volume of Right Prisms. Okay, so you are going to be using this formula that you may or may not remember. V equals B times H, okay, to determine the volume of a right prism. Okay, and if you remember, one little difference, one very important point, when we say B, we are talking about the area of the base. Okay, the area of the base. So I wonder sometimes why they didn't put A of the B or something like that instead of just B. Anyway, yeah, so area of the base. We're going to use that formula to calculate volume of right prisms in this lesson. Okay, you did this, or you learned this, or introduced to this in Module 3, if you remember, around Lesson 23. You learned that a polygonal base of a given right prism can be decomposed into triangular and rectangular regions that are bases of a set of right prisms, okay, that have heights equal to the height of a given right prism. So, and I'll show you what that means in a second, okay? All right, so let's get going here. All right, so this opening exercise here, it asks you to go ahead and take your copy of the following figure out of your binder and cut it into 4 pieces along the dotted lines. Okay, and you can see those right there. All right, and that vertical line there is what's called the altitude. Okay, and that's the very maximum height of that larger triangle. And I'm not saying you have to actually do this, okay, but if you want to, you can, and you'll see what's going to happen and manipulate it, okay? Now, the horizontal line joins the midpoints, and that's really important in this case. It joins the midpoints of the 2 sides of the triangle, okay? So, you know, these 2 points right here, that point and that point there, they are midway between these. So these 2 sections, these 2 pairs of sections here, these 2 they're even, and these 2 here are even. Very, very important that is the case, okay? All right. So if the question here is, now again, what they wanted you to do here, if you cut this out, you can just arrange the 4 pieces up here. So you arrange the 4 pieces so that they fit together to form a rectangle. And I think some of you can see how you do that, okay? We'll do it again on the following page. So, but here's a question though. If a prism were formed out of each shape, and I'm reading from down here, the original triangle and your newly rearranged rectangle, and both prisms had the same height, would they have the same volume? Okay, so if you made, the question here is, okay, if you went ahead and made a prism out of this, okay, so if let's go ahead and do that. Okay, so you made a prism out of that there. Okay, if you made a prism there out of that, or you made a prism out of this new rectangle you would make here. So you can see that this would no longer be here, okay, but this would be like that, okay. All right, so those 2 prisms, the one I made before and then this one right here, the question is, would they have the same volume? Okay, so what do you think about that? Think about that for a little bit, okay, and let's move on. All right, so here we are again with our blown up version of that triangle from the previous page. Okay, so if I do go ahead and take those 2 pieces like I had mentioned, okay, that right there, that rectangle is going to have, of course, the same volume as that original triangle, okay, because you haven't changed anything yet. You haven't changed any pieces, okay. They are the same size pieces, or just being put in a different place. And again, that's the whole reason. Ken's a really good example of the relationship between triangles and quadrilaterals. Okay. Now let's go ahead and take a look at these here. Okay. Now vertical slices through a right triangular prism show that it can be cut and rearranged in a right rectangular prism. Okay, and you can see right here we have a right triangular prism here. Okay, this piece, these two pieces here have been cut off separately, and you can see they've been placed here, and then this one over to here. Okay, so you can see that nothing has been lost nor gained. It's just been kind of just moved around. Okay, therefore they're going to have the same volume there. Okay, now these two here, these two shapes, and again it's the same exact thing. That is just that without the pieces cut off. Okay, so in this sense, the triangular prism and the right rectangular prism have the same base area, the same height, and the same volume. Okay, so they have that same base area here. Here's the base area, and here is the base area here. Okay, same base area. They have the same height. Okay, in this way, and this going to be probably from there. Okay, the height there, and therefore they have the same volume. So in volume terms, they are going to be equal. Okay, and so now this this union of right triangular prisms have the same height here. So everything has the same height. So all these, there's several right triangular prisms here. There's one, another one there, 2, 3, 4, 5. So 5 different right triangular prisms. Okay. So now the volume of all of this is going to be the sum of the volumes. Okay. So each one of these right triangular prisms is going to have a volume of its own, okay, and therefore the total volume of this larger figure here is going to be the sum of all those volumes, okay. And the way we get those volumes is by using the volume formula that I mentioned when I first opened up this this lesson, and that equals base, and again that's the area of the base times the height. Okay, so we have an area. We can figure out the area of all these bases. Okay, all these bases, and we can then multiply each of those by the same height, because they're all, as you can see, all have the same height. Okay, all right. Get the volume of each of those. It's going to be the sum of all those volumes. Is going to be the total sum of this larger shape. You know, and more importantly here, we can take the actual sum of all these base measurements. So we could take this base measurement, this one, this one, this one, and this one. Okay, so you take the sum of base measurements, and then all we have to do is multiply that sum by the height. Okay, because they all share that same height. Okay, therefore we're not taking the base of this one here, for example, then multiplying it by the height, and then taking this base, multiplying by the height. All we have to do is just sum all of these bases up, sum them up, and then that sum of all those bases, okay, is going to be multiplied by that common height, and that will give us the volume in, of course, cubic units of the entire figure. Alrighty, so here we go. We are at exercise 2 here. Okay, and exercise 2 asks us to show that the following figures have equal volumes. Okay, show that they have equal volumes. Well, you can tell what has been done here, but we should go ahead and, of course, prove this. Okay, so step number 1. Okay, let's just have our put together here our we're working on that the right triangular prism there, okay, and half base times height is going to give us our total volume, okay, and we have 8. You can see we have 8 and 9 as our base and our height, and we put that right there, okay. So this is actually half. 8 times 9 equals, I just want to put 1/2 here, 1/2 of 72. I'm not doing anything with that half yet, okay? All right, and so next step, all right, so times 8, okay, so if I multiply 72 times 8, okay, and again I'm doing that because I'm getting that from here, because that is the height right here, 8 centimeters, okay, that's the height. And so I still have to pay attention to the half. I haven't done that yet. So if I know I have 1/2 of that, I'm going to divide that by 2, and therefore I get, excuse me, 288. It's not square centimeters. I made put that wrong thing there. This is cubic centimeters. Okay, all of these are cubic centimeters. Okay, and I made that same mistake here. Okay, so cubic centimeters. All right, cubic centimeters. We'll talk about volume. All right, and again, the way this works is if you took this triangle, for example, here, okay, and what you're doing is you are just kind of splitting it up into units. Here you go. You have a height this way of 8 centimeters going down this way. So I'm taking this base, and what I'm doing is I'm taking the area and keep on taking another area piece, another area piece, another area piece, another base area piece. Keep going all the way down. All these little chunks here, what's being done is they're being added together. Okay, being added together. In this case, all I need to do is just multiply by my 8 centimeters, and my base here that I get, my base area. Okay, and that area, of course, is going to be in square centimeters. All right. And then when I multiply it by 8, okay, then it becomes cubic centimeters, because that's my third dimension, okay? So it's another nice way, a very handy way to actually figure out volume of a three-dimensional figure. Heck of a lot easier than having to remember all different kinds of formulas, okay? Anyway, so there we go. We have that's 288 cubic centimeters. Okay, we take a look at this one now, a little bit easier, because all we need now is base times height, then times the actual height of it again. Okay, so we're trying to figure out, firstly, we're trying to figure out this here. Okay, we're getting this measurement first. Okay, that's our area there, and that is 8 times 4.5. Okay, because here we have 8 right here, 8 across, and then it's 4.5 this way here. This is 4.5 centimeters there. Okay, so that's 36. So now we know, and again, this is 36 square centimeters. All right, and that's this part right here. That's the area right there, or the surface area of that section. Now we're going to multiply that, of course, by 8. Okay, right over here, and if we do that, we get 288, not square, but I did these annotations before and messed up, cubic centimeters. Okay, and as you can see, the area, or the volume of this right triangular prism is the same as the area, the volume of this right rectangular prism. Okay, again, simply because we've actually just taken the pieces and just rearranged them. Okay, if you're going to rearrange pieces on a geometrical figure, you're not going to change, in this case, you're not going to change the volume at all. Okay, and how can it be shown that the prisms will have equal volumes without completing the entire calculation? Well, if you actually had these in three-dimensional form in front of us right now, we could do what I've been talking about here, is actually remove a couple of pieces and rearrange them. Okay, so in fact we would be just actually removing, we could remove these dark brown pieces here and place them there and there. Okay, and that rearrangement would prove their equal volumes without actually doing any calculations at all. Okay, so here we go. Example 1, calculate the volume of the following prism. Okay, so I'm going to recommend that you go ahead and decompose this prism into two parts, and if you take a look at it, it's two natural parts to actually decompose. So go ahead and do that with what you know, and come on back and check in. Alright, let's go ahead and take a look at this. So when I had suggested this idea of decomposition, I was taking this kite here, this kite form, and actually breaking it up into two triangular prisms here. And we'll work with this first one here that I've outlined in purple. Okay, and we have 1/2 18 times 20, and of course what I'm trying to find here is I'm trying to find the base, the area of the base right there, and so that's 1/2 18 times 20. Okay, and if we do that, we have 180 square centimeters. Okay, 180 square centimeters, so that top bit of surface area is worth 180 square centimeters. And now I take into account the height of the prism, okay, and I multiply therefore by 3 centimeters, and my answer here is going to be 540 cubic centimeters. Okay, so that is the volume, very simply done with our volume equals base area times height of that one portion, that one triangular prism. Okay, so now we can go ahead and do the same for the second triangular prism, that smaller one back there. Same idea, find the area of the base first in square centimeters, multiply that by 3 centimeters, which is the height, and I end up with 108 cubic centimeters for that portion of this figure. Only thing we have to do is add those two together, and I get a total of 648 cubic centimeters. Okay, so here we go. We have example 2. Example 2, not using an illustration or an image in front of you. You just need to work with the description, and well, actually, I will provide you an image of this pentagonal prism here. But anyway, this is what example 2 asks for. A container is shaped like a right pentagonal prism with an open top. Okay, when a cubic foot of water is dumped into the container, the depth of the water is 8 inches. You need to find the area of the pentagonal base. Okay, so what we're trying to find out is we're trying to find out just the area of the base. Okay, working with what we know the depth of the water, which is going to be our height. Okay, the height of this pentagonal prism. One thing I wanted to make clear, now this water that we're dumping into this container, it actually fills the container. It's not it's not actually written here that it does fill it, but it does indeed fill the container. Okay, and there is that container. Okay, again, just to assist us here in figuring this out, I have supplied you here with a pentagonal prism container. So if you go ahead and work with that, and you can maybe draw your own pentagonal prism and figure out what the pentagonal base of this prism is, and come on back and check in. Okay, let's go ahead and solve here. So what we know, it's going to round up everything that we know first. We know the volume. That volume equals base times height, and again, that base is the area of the base, okay, times the height of the container in the set in this case, okay, and that is that area right there. Okay, so that's the volume of that base times the base right there. That's the base. Then of course the height again is how high this container is, and that right there. So this is what we know. We know how to calculate volume of this pentagonal prism. We also know that the volume of the prism is 1 cubic foot. Okay, 1 cubic foot of water. Okay, is going to fit into that pentagonal prism. All right. Okay, and there we go. I just wrote in that 8 inches, and we also know that that 1 cubic foot of water, when it fills up that pentagonal prism, it will fill it up to 8 inches. So it's 8 inches high. Okay? Okay, so now we're going to go ahead and put together an equation. All right, because we're trying to solve for h. Okay, actually, we're not trying to solve for h. We're actually trying to solve for b. Actually, trying to solve for the base. Okay, that base area. All right, so we'll write our equation. So we have 1 cubic foot is equal to base times 8 over 12 feet. Now, the reason I did that is that we have been given the height here in inches. All right, we have been given the volume in cubic feet. Okay, for us to keep this reasonable and do as little converting as possible, we can start right away and start off with our conversion. So 8 inches is going to be the same as 8 out of 12. Okay, 8 out of 12 inches. So 8/12ths of a foot. Okay, makes sense. We can look at that and say, hey, this does make sense because 8/12ths of a foot is less than 1 foot, and we know that 8 inches, of course, is less than 1 foot as well. Okay, now that 8/12ths can be simplified. All right, it's good to do all of this now, convert now, simplify now, so we don't have to do it at the end. We could turn that into 2/3 of a foot. So what we come up with here is we have our initial equation. 1 cubic foot equals base times 2/3 foot. Okay? All right. And then to solve that, of course, we're trying to isolate the b, because that's what we're solving for, the base, and we'll divide by we'll divide by 2/3. Okay, which means, of course, multiply by the reciprocal. All right. So if we divide 1 foot over here by, I need to, let me erase this first here. Erase that. Okay. And, okay. So what we end up with is 3 over 2 square feet equals b. Actually, it should be cubic feet. Okay, equals b. All right, and there we go. So 1.5 or 3 over 2 cubic feet. Actually, let me take that back again. This is square feet. I'm confusing myself because we are actually solving for the base. Okay, we're solving for the base, and the base is an area number, and that area figures, of course, is going to be in square feet. Okay, so what we know now is that base right there is 3 over 2 or 1.5 square feet. Okay, then I want to go back here and just do this for you here. So when you divide, just to remember here, when you divide by 2/3, what you're actually doing, okay, is you are, put this 1 out of 1, you are multiplying by 3 over 2. Okay, when you divide by a fraction, if you remember, you are multiplying by its reciprocal. Something we've done, and it's been quite a while since we did this. So that's going to equal 3 over 2 here. Of course, if I did it with 2 over 3 multiplied by the reciprocal, it would be 3 over 2, which equals 6 over 6, which of course is 1, which leaves us with just b here. Okay. So now what we can do now is we can go ahead and plug in this 3 over 2 here, just to keep checking. 3 over 2 square feet into our volume equation here. So let's go ahead and do that. Let's get rid of all this. And we'll go ahead and put, so 1 cubic foot should equal, therefore, 3 over 2 square feet times 2 over 3 feet. Okay? And again, this is 2/3 foot is actually that 8 inches converted. So here's our height, here's our base that we solved for. And if you can see that, 3 over 2 times 2 over 3 is actually 1. Okay, so that is actually going to be 1. And then cubic foot, and a cubic foot again because we are multiplying a square by just a 1 foot, to the first power, and therefore we get cubic feet. Okay, and there we go, and it solves it. It checks. All right. Okay, so example 3 now. Example 3 says we have 2 containers that are shaped like right triangular prisms, and each with the same height. Okay, each with the same height. Now the base areas of the larger container, is 200% more than the base area of the smaller container. This is hearkening back to our percentage module, which was module 5, and I think it's module 5. Yeah, module 5, where we talked about 200% more, 200% less than. So all of those. This is going to actually ask us to bring that back to the front. That's why you can see this module truly is kind of picking different aspects of the modules that preceded it and kind of tying them all together here. Okay, and we'll talk about that again because again these are things that happened that we did some time ago, and of course easy to forget. So how many times? Here's the question here. How many times must the smaller container be filled with water and poured into the larger container in order to fill the larger container? Okay, very simply, if we have a small container, a small triangular prism right here, all right, and then we have this larger one, which they're telling us is 200. Whose base area is 200% more than the base area. So how many times do I need to fill this with water and then dump it, then fill it again and dump it? Okay, so how many times would I need to do that based on the criteria here, based on the fact that this larger right triangular prism has a base area that is 200% more than the base area of the smaller container. Okay, so that is our question. Let's go ahead and take a look at that. Rather you not do that quite yet because I do want to explain this idea and just to remind everyone about this idea of 200% more. Okay, 200% more. All right. Now, with 200% more, it's easy enough to say, okay, so if you had 10, say you had 10 milliliters in something, okay, and it's easy enough to say, oh, 200%, okay, oh, 200%, it's the same as, oh, 2 times, okay, 2 times, and then I'll just multiply that by 2, and then I'll get 20 milliliters, okay. Now, the problem with that is that we are talking about 200% more. What we haven't accounted for in this case is the fact that we started off with that. We started off with that 10 milliliters. Okay? 200 times, or 200% of this 10 milliliters here is 20 milliliters, but that's 20 milliliters more. Okay? Therefore, we have to add back that 10 milliliters. Okay, so we start with the 10 milliliters. We have 20 milliliters more. and we end up with 30 milliliters. Okay, so again, the rule here, or the trick, or the tip here, is if you see 200% more, just go ahead and multiply by 3. Okay, and you can see where you get to that answer right there. If we multiply 10 milliliters by 3, we would get to 30 milliliters. And this is tricky stuff. And again, this was handled, or we talked a bit about it in Module 5, probably early on in Module 5. But again, these are things that are not so easy to remember, because they seem a little bit counterintuitive. I mean, why do you multiply by 3 when you're talking about 200% more? Well, you can see why now. And again, the way it's worded is always going to matter greatly. Okay? So again, here we go. So that 200% more means times 3, okay, or times 300%, okay? So the base of the smaller prism, let's let that equal B, okay? We're gonna, because we don't have any other numbers, okay? We don't have any actual measurements, all right? So we have the small base of smaller prism equals B. So therefore, because it is 200% more, or 200% greater, the base of the larger prism, we are going to assign it the variable 3b, because it is 3 times the base of the smaller prism, okay, because it is 200% more. All right? I know, sounds confusing, but you'll get used to it eventually. All right, so the volume of the smaller prism is going to be, and again, I've just added this A here, is going to be the area of that base times the height, okay? And we know they have the same height, okay, which is really important, right? And then the volume of the larger prism is going to be 3 times the area of the base times the height, okay? The only thing here that has changed is the fact that I am multiplying this exact equation here, see it? Multiplying it by 3. Therefore, the volume, if the volume is 3 times greater, and let's say we started off with 10 milliliters, and then we have it's 3 times greater, we're going to need to actually fill up that smaller container 3 times and dump it into that larger container, okay, to fill it up. Okay, and again, if we take our 10 milliliter example, okay, that 10 milliliter container, it's going to take 3 of those to fill up a 30 milliliter container. 1, 2, and then 3 times. Okay, so again, just real purpose of this problem, again, to kind of look at these 200% problems all over again, and use the formulas for volume, use what we know, and again, not even the only number we were given was the fact that we had 200% more in the a base of 200% more on that larger container. Okay, so let's see what we can do with this, with the next. Well, there we go. And that small container will need to be filled and emptied 3 times. And that would be the answer. Okay, so here we go. Why don't you try this one out? I'll just read it for you, and then I'll pause and have you decide who is correct. Okay, who is correct here? So we have 2 aquariums are shaped like right rectangular prisms. Okay, get that image into your mind. A right rectangular prism, not like most aquariums are. All right, and then the ratio of the dimensions of the larger aquarium to the dimensions of the smaller aquarium is 3 to 2. Okay, so the ratio is 3 to 2. Now, really, really important here, and I'm just going to underline it just to help you think about it, the ratio of the dimensions. Okay, the ratio of the dimensions. That's really important when we're talking about volume now. Okay. All right, so here we go. Addie says the larger aquarium holds 50% more than the smaller aquarium. Barry says that the larger aquarium holds 150% more water. And finally, Kathy says that the larger aquarium holds over 200% more water. Your question here, are any of the girls correct? Then explain your reasoning. Okay, so do whatever you need to do, draw a picture, crunch some numbers, and again, that ratio is real important, 3 to 2, and again, remember, we are talking about the ratio of all the dimensions. All the dimensions, my last hint. Okay, so go ahead and struggle with that and see what you can do, and come on back. Okay, so let's go ahead and start here with our solution. Firstly, and most importantly, is paying attention to the fact that we have a ratio of 3 to 2. Okay, and again, a ratio of the dimensions. I did not expect this to be easy, simply because, again, as I mentioned before, it's been some time since we've worked with these ratios and percentage expansion and deletion. Okay, so but anyway, so we have 3 to 2 written as a ratio that way. What's very important is also to remember that ratios can be written in several different ways. Okay, 3 over 2, while yes, it is a fraction, is also a ratio. Okay, and a lot kinder and gentler to work with at times, as is 1.5. Okay, 1.5 is also a ratio. Okay, it is 1 1/2. All right, these are all equal to each other. The ratio of 3 to 2, 3 over 2, and then 1.5 as a decimal. Okay, and again, underlining again this idea of the ratio of the dimensions. Okay, each dimension, and when we're talking about volume, we're talking about 3 dimensions. Okay, 3 dimensions. All right, therefore we need to account for all 3 of those dimensions. So we know if each one is going to be 3 dimensions, we need to multiply 1.5 times 1.5 times 1.5. Okay, so this ratio of 1.5, or 3 to 2 here, needs to be multiplied by itself 3 times. Okay, so 1.5 times 1.5 times 1.5, and that leads to 3.375 times greater, or 337.5%. Okay, or 337.5%. Now we're not over yet. I'm not done. Okay. Now this is the same as 237.5% more. Okay. It is 237.5% more because we need to account for the 100% already of the original. So, but that, anyway, that 237.5% is pretty much what Kathy was saying, because Kathy is correct, because she said very correctly that the larger aquarium holds over 200% more water. Okay? Again, and this was the tricky part, right over here. Okay? The ratio of the dimensions of the larger aquarium to the dimensions of the smaller aquarium, 3 to 2, the dimensions. Okay, there are 3 of them. Therefore, this 1.5 needed to be multiplied by 1.5 times 1.5, giving us this. Therefore, we have 3.375 times greater, okay, or actually it should be 3.375 the size of the smaller, okay, so actually 3.375 times the size of, right, which is really important, actually a very strong distinction, okay, or 337.5% of the smaller one, okay, and that's the volume. We're talking volume right here, okay. So all of these, this refers to the volume here, okay. This is the volume right here. That's refers to the volume. This 1.5 refers to each and every one dimension, okay. The height, the length, the width, okay, all three of those. Alrighty, so ending on that note, there we go. That was a tough one. I'm sure they'll throw one of those at you in the in your problem set. So hopefully you took some good notes, and I explained it well enough to have you do well when you see that again. So this, in the lesson summary here, probably one of the most important things, or most beneficial things we learned or we saw, which we actually saw some time ago, again, a few units ago, or a few modules ago, is that the formula for the volume of a prism is V equals base times height, where B is the area of the base of the prism. And again, this is so important, okay? B is the area of the base of the prism. And again, I'm not quite sure why they don't write that a little bit differently. I would love it if it was, V equals A of B times H, for example, with A, of course, being area. But anyway, that's what we have right here, and you'll probably see it that way in the future, so you need to get used to it. Also, a base is neither a rectangle nor a triangle, or excuse me, a base that is neither a rectangle nor a triangle must be decomposed into rectangles and triangles in order to find the area of the base. Okay, and that's when we saw we had the that kite figure. Okay, the kite shape like that. Okay, we decomposed it. We looked at it in terms of this triangle here and this other triangle over here. Okay, so again, this idea of decomposition comes up over and over again when we're working with shapes that are somewhat out of the ordinary. Okay, well, there you go. That's it. That's lesson 24, or 5. I'm sorry, 5. 2 lessons to go. Good luck on your problem set, and see you again.